All right, so I'm going to talk a little bit about how shocks can play a potentially important role in the observed properties of stellar mergers. This is not based on a lot of detailed simulations, so certainly some of it is open to debate. But I think the main thing I want to emphasize is that I think circumstellar interaction, namely the interaction between different components of ejecta and stellar mergers with previous material, is actually a really efficient way to power transients, because you can get an energy per gram, which is something like the shock velocity squared, which in some cases can be quite high, say, compared to what you would get from recombination. So we have to think about shocks as an important source. So we heard a little bit of this yesterday. This sort of diagram of peak luminosity and time scales, and the fact that down here we have the nova, which are dim things, and up here we have the supernova, and in between we have these intermediate luminosity events. These include the so-called luminous red nova, which are optically detected transient events with durations of hundreds of days or even years. But then we also have, from Monsi Casawal's Spitzer survey, these new events called sprites, which are basically transients, as far as we can tell, just produce infrared emission. They're highly dust obscured, and we don't know what they are, but they may be related to stellar mergers. With the luminous red nova, we know, we have good evidence that there are from stellar mergers. So these are some of the optical light curves of stellar mergers. Not all the data is perfect, but what I just want to emphasize is so that you can see that they come in a range of different luminosities. They have a range of different timescales. Sometimes we have good observations before the sort of peak of the luminosity, and other times we don't. But we see some common features, like the fact that many of these have precursor, or at least some brightening of the event well prior to the event itself. And then when you have presumably this is the time of the dynamical phase of whatever is going on, you'll often see in the light curves that there will be two peaks. There'll be an initial peak and then a secondary peak. This is not always seen. There are some cases, like in 1309 SCO, where we don't see the second peak, but this is pretty common in these types of events. So I just want to talk about, so basically what my talk is addressing are what are the different things that could be powering this emission. Is it a cooling envelope emission, namely is it just the fact that we shock heat and eject some very hot material, and as it expands into space, it radiates energy? Is it the fact that as this matter is expanding, it recombines, and that releases some energy that powers the light? Or could there be shocks in the event, either prior to the dynamical phase or after, as the dynamical material plows into whatever was ejected prior to the dynamical phase? I'm going to talk first about the precursor stuff. So we all know this well-studied event, 1309 SCO, where we saw the binary was observed for almost a decade. The period was shrinking with time as the two stars were approaching merger. And also, as time went on, it got brighter near the end, up to this event, which would have been classified as a luminous red nova, albeit one on the dimmer end. And then, of course, we had this interesting observation of the phase light curve, which showed sort of double peaked, what you'd expect for a contact binary. But then approaching the time of the merger, the profile evolved significantly to where there was basically just a single photometric peak by the time here before the final dynamical phase was starting to get underway. And so Andre's done quite a bit of work trying to argue that these sort of features of 1309 SCO are related to can be related to the fact that if you just assume that during the final stage of this merger there was some mass outflow, for instance, from the L2 point, that carries away angular momentum and can cause the binary orbital period to shrink. But it also ejects material, and this material shocking on itself, for instance, can produce some of the brightening that we see at the end. So basically what we're seeing is a sequence of ever-increasing mass loss rate as this unstable mass transfer is starting. So this is just a simulation from some simulations that Andre did, where he's studying what effect the obscuration from mass leaving, for instance, the L2 point has as you increase the mass loss rate approaching the merger, and how you can turn what is a double peaked profile into something which basically you block one side of the star with the matter coming out of L2, and can produce this evolution in the phase light curve. And so I don't want to go into this much detail, but basically as you increase the mass loss rate, you can explain this evolution going from 2001 to 2008 observed. And then after this point, the the periodicity went away. The whole thing was so obscured with whatever was coming out that we no longer could see any periodicity. Nevertheless, you can try to empirically estimate what is the mass loss rate prior, this is time prior to the merger. And since you know some properties of the binary, given a mass loss rate, how much that should cause the period derivative to change from angular momentum loss. And so you can compare that needed to explain the evolution of the phase lag curves with what you observe for the period, and you can get a sort of concordance picture for mass loss rate happening at this rate, 10 to the minus 5 here and going up to 10 to the minus 3. But then, beyond that point, then what explains why the fact that it's sort of ramping up in peak brightness towards the dynamical event? Well, here the idea is maybe there could be shocks between these outflows that are coming out of the L2 points. So for instance, there's a simulation from Andre showing that you have matter coming out of L2. As it goes out, it creates a spiral pattern, and there are internal shocks within that which can produce quite a bit of luminosity. And if there's different regimes depending on where the tidal tails are optically thick and thin, and that emission can come out directly, or whether you have to diffuse out. And this is something that Andre has explored in some detail. And essentially what he finds is that, if you do these simulations, you can reproduce the observed, beyond this point where we can no longer see the periodicity, you can continue to infer that the mass loss rate, say out of L2, is ramping up near the end there. And when he does this, he sort of integrates under this and finds that, pre-dynamical ejecta mass could be maybe significant, maybe several percent or even 10% of the solar mass. And these stars were about a solar mass or so in total. So this is a sizable amount of mass that's coming out well before the actual dynamical phase. This is the lead up to the runaway. Okay, so that's the basic picture that we have for what's happening before here, that these precursors are the fact that this dynamical runaway mass transfer happens over many, many orbits and builds up. Maybe there's some time of internal dissipation. Okay, so then what powers the peaks in the lag curve after that point? One possibility which Natasha discussed is this idea that this is just material that's ejected during the merger, and it's the recombination, very similar to a type 2 plateau supernova. And I think that's a very interesting idea, and probably is relevant here, it's definitely in some cases. But there are these sort of two peaks, and so you could say, well, are there two mass ejections from this merger, one, separated by some period of time, as we heard sometimes the simulations show earlier today, or would there be another mechanism that could produce these two peaks? So I think Morgan introduced this idea that the first peak could well be the cooling envelope emission from the fastest dynamical material, and he makes an argument in his paper for M31 2015 that recombination has a lot of trouble explaining this first peak, but if you just hypothesize that the two stars merge and you eject a fair bit of mass, basically the idea is that the matter that is freely flying out, say in the polar directions, as it cools, that thermal emission can escape, and you can explain the luminosity that way. I'll let him talk more about that. This is from his recent simulations. And then, but the point I want to emphasize is we have evidence from the pre-merger that there was a lot of mass loss leading up to the dynamical phase, and so any dynamical ejection mechanism will have to go through that material. Now, if it's equatorially focused, as we expect, then in the polar regions it will freely expand, and so it could produce this first peak in the emission, but then in the equatorial regions it's going to run into this pre-existing spiral pattern of material, and that material is fairly optically thick, so if you shock heat that material, it's going to release a lot of kinetic energy, but it's not going to get out immediately because it has to diffuse out of this dense torus. And so there's a second time scale. There's a sort of diffusion time scale associated with the fastest material, and then there's a diffusion time scale associated with the slower swept up shock material. And so we explored this idea by doing a very simple model, a two-zone model, where basically we have a fast flow, homologous flow running into an equatorial region. We calculate how much energy is dumped into the shock, and we sort of basically then calculate the diffusion time of this material up here and this material out here. And by combining that, you can make a sort of, and you include the relevant opacities, you can make sort of toy model of the light curves. And this is just one example where we had a 10 solar mass star, binary separation of 30 solar radii, There's a lot of parameters in the model, but we're assuming here that the amount of ejected mass was like 1/10 of the mass of the star, and that this spiral of runaway mass loss before the merger was over a time scale of, say, 10 orbital times. And so you see this basic effect. So the shock luminosity itself is just kind of dropping as the shock goes out, but then not all of that is actually getting to the observer. Well, this is the fast material, the sort of heat of the polar material that's producing this first peak emission, as we saw. But then, this shock power you're dumping into the equatorial shell takes some period of time to diffuse out, and so you get this kind of second timescale peak. And then as this matter goes out, eventually it gets cold enough that it will start forming dust, and because the shocks have highly compressed the material, it's going to be a natural place to form dust in these systems. And so that's the idea, is that maybe the fact that we see the second peak is not because of two distinct ejection mechanisms, but maybe it's the fact that the stuff you ejected here has to plow through the slower stuff, and its light has to diffuse out more slowly. Anyways, you can do this you can vary the parameters, the mass of the binary, the separation, the time of runaway, dynamical runaway. In some cases, you don't get the second peak because basically the shocks can't keep the gas hot enough to stay ionized, so it no longer traps the radiation, and so you get weird things, which are an artifact of the simplified model, where you don't get a second peak because basically there's no opacity left in the shell. It's too cold. And in this case, in fact, you may get a second peak, but it would be in the infrared because this material has formed dust, and we're not accounting for that opacity here. So that may explain, for instance, some event 1309 SCO, which didn't have a second peak. Maybe the second peak was in the infrared, or it didn't happen. So anyways, you can construct an analytic model for what the peak luminosity and temperature, effective temperature of this shock-heated component to the emission would be in terms of the binary separation at the time of the merger and the binary mass, and this is normalized to the main sequence radius of the star. So what you find is that, if you want effective temperatures for your emission, smaller systems that have higher effective temperatures, which are going to produce optical transients with luminosities in the range of luminous red nova, you need to be in this range. You're preferentially going to have massive binaries producing more luminous transients, but not ones that are enormously large compared to their main sequence radii. So I think one idea is that the luminous red nova are stars that are either merging on the main sequence, or maybe they're moderately evolved massive stars, probably which actually undergo actual mergers. In fact, this is corroborated to some extent by the progenitor properties. I think Nadia may talk about this as well, but these are different luminous red nova which have had their progenitor properties constrained to some extent, and what you see is that many of them are quite massive, and the radii are not, they're evolved in many cases. Some are in the main sequence, some are evolved, but they're not, the largest stars they could be. Whereas when you're talking about the Monsees events, the sprites, these may be the ones that are up here that are much larger giant systems that are going to produce these transients that have lower effective temperatures, and may not even produce any optical emission at all, because basically the material that's ejected in these tails immediately forms dust, and so you have this big dusty tail through which the radiation is diffusing. Anyways, I'm going to finish there. I don't have a whole lot more. I just want to say that I'm motivated by all this because I've studied other systems where I think there are direct analogs of this, particularly classical nova, where you have an outburst from a white dwarf, and it starts overflowing the Roche lobe with the companion star, giving you some kind of slow equatorial torus, and then at some point the outflow becomes much faster from the white dwarf and goes off into this slow torus. And in this case, we see the exact same thing, brightening of the classical nova as you eject matter slowly, and then you turn on the fast engine, which in the case of mergers would be the dynamical phase, and you suddenly start getting shocks that are powering the optical emission. And in this case, we know it's shocked because we see gamma rays from Fermi at the exact same time correlated with the optical emission. So this is a case where it's very clear that circumstellar interaction is powering the optical emission. So basically finished, my conclusions are, I think it's still from Andre. My basic point is I think recombination can play an important role in these things, but I think shocks can outpunch their weight because you get a lot more potential energy per gram if you shock material than from recombination. I think you can explain these luminous red transients potentially this way if you assume that leading up to the event and afterwards you inject comparable amounts of mass, maybe 1/10 of the mass of the star. So you can explain the luminosities and temperatures of these things. In some cases, the shocks may not be powerful enough to keep the matter ionized, and therefore not enough to produce a second bump in the optical, but in that case, probably you're forming dust, and so the second bump would happen in the infrared, and these may be the origin of these Spitzer transients. And I think the general picture that's emerging is that when we have more compact progenitors, those may be the ones that produce these optical luminous red nova, whereas more puffy, bigger things, cooler things may be the source of these infrared transients. And obviously there's a huge amount of work to try to connect this phenomenology to the simulations. And I think the one message I would have for people doing the simulations is that you have to think about what happened before your simulation started, because that may create an environment that really affects what these things appear. You know, if you blow off your common envelope into pre-existing shell of material, that's going to have a big impact, not just on the morphology of that shell, but also on the actual light curves and colors and things. So I'll finish there. Thanks.
So only one question while Nadia says that.
Go ahead.
I have a question about the last point, the view and angles. I just like how it will change if you look through the disk or from the pole. So for 50-9 score inclination, I believe is 70. I don't know how 70 is calculated with the thickness of a disk, but I think it's a margin. So how does it change if you look through the disk compared to the?
Yeah, it's a great question. I guess I would expect naively that it would be dimmer if we were looking through the disk than if we were looking at pole, because the radiation, you're not seeing as much that's able to get directly to you. I would guess that it would also be redder, but I have to think about this more. I think it's complicated because the idea is that you're seeing is a combination what's diffusing out of this fast polar material and what's coming out of the disk and then going through the fast polar material. So it could be more isotropic than you might guess, but yeah, you have to work.
All right. So next is Nadia.
James? Is there another question?
Yeah, there was, but like we
Thank you.
Well, hi everybody. My name is Nadia. I guess I'm the observer here. I'm currently a fellow in the Dutch University at Radboud. So basically, I moved there because I have a good bunch of experts in like stellar evolution and binaries, which is great. So, well, here I would like to provide an overview of some ongoing work on some recent luminous red nova. And that is the name that at least I prefer for these objects, because I think like the community now is moving to call intermediate luminous red transients to these kind of electron capture-like objects with dusty progenitor. So basically, I think I will refer to them as luminous red nova or mergers. So here is a bit of history. So basically, this guy here shows the first detection of a luminous red nova in history, which was made actually 30 years ago from Palomar. So they discovered this red variable in M31 in the bulge that was not there before. They took some spectra and they were really puzzled, but that field was quickly forgotten because no more objects were discovered up to several years later. So basically, how many supernovae have been detected in the last 30 years? I mean, thousands, right? So in my next slide, I have a complete analysis of all the luminous red nova discovered in the last 30 years. Okay, here we go. Our own galaxy. Here we have all our famous objects that we have been exhaustively studying so far. The famous 1309 SCO, which was the eclipsing binary. This guy, which did not have really pre-explosion data. V838Mon, and another one which could be potentially associated with a merger of an evolved star, which is the Ogle one. However, we are slightly better off if we are looking outside of our own galaxy, as we are not constrained by dust. So the picture outside of our own galaxy improves just slightly a bit better. So we have events which correspond to more massive progenitors generally because, well, the envelope masses and the luminosities are higher. So basically, we potentially can observe these massive mergers up to 30 megaparsecs, provided the depth of the current surveys. So basically, using these galactic mergers, as a starting point, Kochanek in 2014, he estimated the rates of stars depends on their masses. So basically for a lower mass, such as the progenitor of these objects, he estimated that we should see one every 10 years. Well, we should hunt really hard for our own galaxy. V3 is every 40 years, but for a more massive star is one every 100 years, which is kind of comparable to the rate of core collapse supernova. So we have been estimating the rates for this luminous red nova in transients such as the Zwicky transient facility. And our estimate based on these rates was that we should be able to detect between 5 and 10 objects. But however, the only object that popped up last year was in NGC 45, and it was in the south, so ZTF even could not detect it. So this is a bit unfortunate. However, here I will address these some progenitors in these 3 galaxies over here. So the good news is that we are at very close by distances. So then we are able to actually study way better the regions where these transients are born. And here I marked the location in M101 with this red cross and NGC 45, and you can see that the stellar population is quite young in those areas. So basically we're lucky enough because generally we had pre-explosion or pre-outburst images in those sites. And here, for example, I show an image of pan stars with this red cross, and here it's HST, and here's an HST as well for M31 luminous red nova. So basically we could actually see that there was a progenitor star at the location where the outburst happened and really pinpoint which was the star that underwent the outburst. And this is really lucky because then you can take your favorite stellar evolution model, which here, well, oh sorry. Yeah, so here I wanted to show that once we know that we have the progenitor, how we know that the progenitor was kind of stable. So basically in the example where we could have archival data from CFHT, not from HST, which is very expensive to image like several times per year, but for this object there, NM101, we had a continuous monitoring with other facilities because M101 is it's a nice big galaxy that people like to observe, so basically we had plenty of data. So for the first, so this goes up to 15 years kind of before the outburst. So in this initial phase, what we could see is that the progenitor did not change too much. So we could see actually that there was a star at the location of the outburst, but it did not change too much in luminosity. But in the 5 years before the outburst, there was this precursor phase that Brian just mentioned, that we could see that basically the photosphere of this star was expanding and cooling. And finally, we saw the peak, so we could really pinpoint where was the progenitor. And here was an extensive follow-up in optical. These are infrared, and this is Spitzer mid-infrared in 3.6 and 4.5 microns. So basically, at the later times, we put a lot of effort in imaging in the optical with Keck, but we just saw that this star disappeared, which is kind of the proof that that was the progenitor, but the star remained quite bright in the infrared. So we kept our monitoring with Keck and Spitzer. So you can play this game and you can just take your favorite progenitor. In this case, we only had like two bands, so you can have to use the color and the magnitude to find the progenitor, and this was like 2 to 5 solar mass star. You can do the same with the other progenitors, and basically what we see here is like most of the stars are in this phase of kind of crossing the Hertzsprung-Russell gap. So they are not, in the main sequence, are not red giants. I mean, here there's a bit of confusion, but basically these stars seem to be in this yellow supergiant phase. That Brian mentioned that they are possibly still quite compact. So that's why we see these optical transients coming from them. So here, this can be a bit of confusion for the loops. But yeah, if you assume that there can be potentially 2 stars which can match the location of your progenitor, one lower solar mass and the other higher, basically kind of this case would be corresponding to kind of the classic literature case B mass transfer scenario. Basically you have a progenitor at the distance of 100 solar radii, and when you start this unstable mass transfer, then basically you will initiate the common envelope. So this is quite nice because, well, we are kind of confirming what was predicted in literature. However, yeah, there is a strong dependency on the models. I took, for convenience, these mist models from MESA, but yeah, I have seen that just varying some of the parameters in MESA can like strongly change what is the stellar evolution in this case. So we have to be kind of a bit careful when interpreting the results for the progenitors. So one of these diagrams that was introduced by Ursula yesterday is this Kochanek diagram, where he used the galactic objects. So basically he plotted the mass of the progenitor versus the absolute magnitude. Here is the V and I band in red. So he used the galactic objects, the 4 ones. However, if we gonna take some of the extragalactic ones and we plot them in the same kind of scale, what we see is that they also seem to follow this trend. So here we have the M31, NGC 45, M101, and NGC 4490. So basically, they do seem to follow this trend, and one of the interesting question is why this is happening, and like why there is correlations. Like naively, you would expect this correlation, but how can we quantify that? So finally, we also followed up these transients. As I mentioned here, they're like the Spitzer point over here in the mid-infrared, and this is near-infrared, and this is the progenitor. So basically, we can see that there was no kind of dusty envelope at about, I think, a few years, like 13 years or so before the outburst. But then we can see that a dusty envelope is kind of forming here up to basically dust masses of like 300 kelvins, are very high masses. So basically, I need to still model very carefully this with dusty, which was actually done for the M31 luminous red nova. And basically here are the parameters derived for each one of the epochs. So basically what we see is like the luminosity of the central source kind of goes down, but the temperature increases. So these are values for the central engine, which is being obscured by dust. So basically dusty assumes kind of a spherical geometry, a certain dust distribution, and also a temperature for the dust, and also like a thickness for the dust shell. So basically, these are the parameters that we are obtaining, that the dust mass is growing, but the central source seems to be getting hotter as well. So yeah, here I would like to just leave my conclusions that so far the progenitors of these extragalactic massive stellar mergers seems to be these yellow supergiants in this KSP mass transfer, but yeah, we have to be careful how we interpret these progenitors because it's very dependent on the stellar evolution models. And we also have to assume that the progenitor was a single star that was not kind of interacting before the moment of the outburst when we observed it. Finally, yeah, there seems to be this correlation between the progenitor mass and the peak luminosity in I band, also for the extragalactic mergers. And we also see this dust formation kicking up as early as like 100 days after the outburst. So dust is important and should be taken into account. Thank you.
Yeah, I think the identification of the progenitors is not quite as straightforward. I mean, I think you alluded to it in the conclusions that, I mean, there could be interaction. In fact, you would expect before they actually merge that there's a long phase which lasts hundreds or even thousands of years, where you have already some temporary common envelope, and the star doesn't look like it would look like as a single star. So I think it's quite natural that they look more yellow, but in reality they might be, the underlying star might be much, much less evolved than you think.
But how could I quantify that?
But I guess the question is are these transients the first contact and the first, I mean,
the mass transfer is not dynamically unstable as such, not initially.
Right. Okay.
You have stable mass transfer.
Okay, I see what you're saying.
Then you start to form a common envelope, but initially the mass in the common envelope is very low, so the frictional timescale is very long.
But will you see it as a yellow?
Well, I don't know what
That's
it looks
the
like,
thing.
but yeah, I mean.
Usually we move to the red once we form this common envelope.
Sure,
And
but
this is
I'm
pretty
just saying
yellow.
it has moved from the blue to the yellow. And it may actually be a blue star.
Yeah, I mean, if I would have a model which says how the star evolves on like this
I mean,
timescale.
I certainly would not expect it to look like what the underlying star really looks like. So I think that can be very misleading. This is relevant because the orbital period you might choose would be wrong. can't give you a solution.
Yeah, it's like, well, I need to make some assumptions, so yeah, that's the best one thing.
Other questions, comments?
Does it depend on the dust species?
I think so far the observations in mid-infrared of luminous red nova, they show that silicates are dominant dust composition.
Okay.
Yeah, we haven't seen further measures of.
Do you have measurements of photospheric radius for these objects, like in the IR?
Yes. I mean, some of the analysis is still ongoing. I started working on this like a month ago.
Anything else?
For M101 is published for interesting for the part.
How much?
For M101 is the published paper.
Oh, sure.
All right. Okay, next up we have Morgan. Okay, fine, perfect. No, so I'd like to go through. Yeah, okay. Maxed up or?
I can do either. I'll talk. Okay, I'll get inside.
All right. I'll give you a 2-minute warning.
That sounds great.
Okay.
Well, thanks for these great talks so far, and I want to talk a little bit about what we've been learning from gas dynamic simulations of this phase just prior to and including those outbursts that we're getting these beautiful data on. And so my dream is that we advance these models to the point where we can put the two on top of each other, ask whether we can infer properties of the objects themselves or the ejecta themselves from the observation. So see whether we can do the reverse problem of extracting parameters from the, just say, photometry and spectra alone. But there's a few steps before we get there. So this is the part that we all agree on. I think everyone has drawn this little dotted line in Keynote. So if nothing else, we understand this about how common envelope phases work. And I want to talk about this stage here where one star engulfs its companion and the outermost skin of ejecta that come off. So we've seen this, and the two things that I think are particularly amazing about these transients are these time scales. So this thing rises from discovery to peak in about 8 days. They have these like extended precursor phases that we were just talking about. And the combination of those things is kind of amazing. So at face value, there's a lot of experts who this won't be a surprise to, but in this particular room, but at face value, how do you have a binary that sits there for 1 billion years evolving, or even 1 million years in the most massive stars, and then all of a sudden it goes wrong in a handful of orbits, and we see some really dramatic transient. So I think that in and of itself is surprising. So I've been modeling these earliest phases of interaction, and we've been talking a lot about simulations, and in this particular case, I made some choices in the simulation that I think are particularly well suited to this part of the problem, but then not well suited to doing the remainder of the problem. So I use grid-based methods, so that lets you follow the volume rather than the mass. So that helps if you care about the low-density volume-filling material. And I actually do this in spherical polar coordinates around the donor. So the dimensionality of the mesh, or the geometry of the mesh, matters when you're trying to keep the star in hydrostatic equilibrium, which is this balance between pressure gradients and self-gravity that's probably the hardest thing to do in an explicit evolution code. So I'm going to show you an example where the donor star has a mass of 1, the accretor star has a mass of 0.3, and it's an ideal gas equation of state. And so here we're rotating in the instantaneous frame that keeps these along the x-axis. What you can see is that there's this stream of mass transfer, and it sets up around the accretor, but then it explicitly in our simulation, we don't allow it to accrete onto that object. In reality, what happens is that it quickly exceeds the rate that it can be absorbed by that object. And it flows away from the binary system. And So there's thin sort of boundary layers of material, and this is what I think Philip was just alluding to in these phases leading in. And then I had to go to like a sports slow motion at the very end because it goes so fast. So what's going on? If we look at the paths of the orbit, it goes from like really tightly wound to this loosely wound spiral. And if we think back to the very first talk of this conference, Natasha was talking about this transition from this unstable Roche-Lobe overflow, very gradual process to a real plunge together of the two objects. One way that I think it's interesting to quantify that is just to ask, over what number of orbits is the separation changing by order itself? And as they come together, as the separation is similar to the original donor star's radius, it's changing on the order of one orbit. Okay. So another way to look at that is what drives the evolution of the orbit is an imbalance of material that's pulling both backward or forward. So here, material dragging the pair backward, exerting a negative torque on the orbit is pink. Material pulling forward is green. I borrowed sort of this plot from folks who are doing accretion onto supermassive binary black holes, many of whom are here in New York. And so if you were to integrate this in the full volume, you would find that that's the rate of change of angular momentum of the binary. And what you see is that as the gas distribution becomes extremely distorted, you get an imbalance of positive and negative torques, and that drives the evolution of the orbit. So you go from a symmetric situation, the orbit evolves slowly, to a very asymmetric one, where the orbit evolves quickly. Okay, and then we can think a little bit about the mass that's coming off. And I think this is really interesting. And I think the first thing that you may notice is that the material that's streaming away from the binary isn't making it all the way to infinity. It's sort of piling up in the surroundings. And I think this has to do with, in detail, the amount of specific angular momentum that is being thrown away from the binary with. And it turns out to be very sensitive to that. And that means that these later and another thing to point out is that the radial velocity of the ejecta increase as they come closer together. And that ensures that these earlier sort of material are continuously interacting with the later expelled gas.
So Morgan, to understand, so the plunging phase is due to the gravitational torques, not due to the friction.
I think they're one and the same thing, essentially.
Okay.
Like there is material, there's an over density behind this star, so it's moving through gas.
Well, I think the difference is that the friction is more perturbative, right?
Yeah, so I think another way to put it is when the binary is separated, you're really extremely far from the situation of like a uniform medium.
Right.
And that's why it often makes sense to sort of talk about it. So these interactions of this gas are exactly what Brian was talking about. And something that we see is that much of the early mass loss is not escaping to infinity. In this plot, I'm calling it bound, and only the latest material coming from sort of separations from 50% outside the donor to as they come together is actually energetically, instantaneously unbound. So I think it's
unbound in the sense of kinetic.
I was waiting for that. So here I'm saying, in this instantaneous snapshot, is the Bernoulli parameter more or less than that?
All right.
So I think there's an interesting change in morphology here from this sort of picture that we maybe all have in our heads of what Roche-Lobe overflow might look like, to as they come together, we've been seeing these sort of broad fans of ejecta and much more mass rich. So in this last orbit, the mass ejection rate from the pair increases by an order of magnitude. And actually, this gas is
Can you
initially
draw the photosphere in that diagram?
If you draw, well, let me come back to that as a first question, because I think that's a really interesting point. So as these later faster ejecta crash into the surrounding torus of material, there's only one escape route, and that's sort of to get reshaped towards the poles. So there's almost a hydrodynamic only collimation towards the poles. So think of equatorial ejecta crashing into something else, it like squeezes out in the polar direction. And so we see most of the mass density is in the equator, but most of the kinetic energy is towards the poles. These are azimuthally averaged around the donor.
What's the mass ratio between those which been outflown before and now ejected?
Sorry?
I mean, you say that it's shaped so much by the disk, but
Yes.
what's the mass ratio? I mean, how much mass will have in this disk, which was created by previous L2, L3 outflow, and how much mass you ejected?
Up until this point, it's about equal masses.
Because that's usually not the case.
Well, so I think to your point about talking about one specific phase of this interaction, I'm looking at what happens when they go from unstable mass transfer to one star inside the other. There's a lot more that happens next. So, and that's a very good point. So I wonder if this just hydrodynamic collimation relates to the bipolar shapes we're seeing of preplanetary nebulae and even later planetary nebulae objects. So one more thing, just because it's kind of fun. If you set up the donor non-rotating, isn't this the weirdest thing you've ever seen? So I thought for a year and a half that this was wrong. It turns out that it's a resonance between the fundamental modes of the donor envelope and the orbital frequency. And so actually, as they come together, you sweep through different resonances, and you see different spherical harmonic patterns on the surface of the star.
So M decreases as you decrease.
Yes, so the resonance condition is M times omega orbit is equal to the omega of the mode. And so you actually sweep sort of downward from higher azimuthal order to lower azimuthal order. This is just kind of a fun thing, and it's actually, you can see it in, for example, I spent a long time rewatching Jose Nandez's videos in this non-spinning case and the spinning case, and it's sort of there a little bit. But that's been kind of fun to think about.
It's the same as Savonai's, de Witt and Savonai's resonant type.
Can you say that louder?
Well, I guess if nobody read the paper better than me, then I better discuss it in private. But I think
Probably related to.
Yeah, Gajan Savonai, there's these tidal modes that if you come closer, at some point, like eccentric binaries, you can trigger certain modes.
Yes,
and,
this is
stronger
absolutely
tidals.
related. This is a resonance between a mode and the, what's sort of unique about it is that because they're very close, you actually couple strongly to a higher azimuthal order, not an L equal 2 sort of quadrupole with higher radial order.
These only happen if Q is
Yes.
pretty large.
I think this tends to happen when the mass ratio is such that the perturber,
Right.
or the accretor, is smaller than the
So kind of
tidal star.
stability.
Yeah, and it has to do with the symmetry of the tidal field about the object. So, I don't know, I'm excited to be here with you all. I've been excited to be learning these past few days, and you know, we're not there yet, but this has been fun to try to simulate and learn from, even just this one sort of corner of the bigger problem. So thanks so much.
Is it faster than you?
Okay, Ursula has a question.
So your L2 outflow is bound, as is ours, whereas in Andre's one, it's not, it's unbound.
Yes,
So since the optical properties may depend on that flow and how it expands or doesn't.
So I think what we find is that the material has slightly lower specific angular momentum and specific energy than that of the co-rotation at the L2 point.
Yeah.
So, and in particular, this is a function of mass ratio, and I've been looking at this with varying parameters a little more carefully, but it's something between the specific angular momentum of the accretor and the specific angular momentum of the L2 point. And so, whereas you know, if you don't simulate the inner binary, you have to pick something, and I think a natural choice was the angular momentum of the L2 point as an injection. But I think that those experiments could be redone with conditions for the outflow informed by a simulation of the inner binary, which is sort of what we're trying to do. So I think a goal could be to ask what the properties are as a function of time, and then feed those into a model of sort of purely the outflow, which is, they could form an ingredient for that kind of calculation.
Yeah, I mean, just a comment about this. So, I mean, the radiative properties of bound and unbound outflows are very different.
Yes.
So the ones that are unbound are way less radiatively efficient. So the luminosity can be measures much smaller, because the things that go out and come back, they shock, and they continue to be perturbed by the binary in the center. So the luminosity can be way higher.
And isn't it sort of like if your luminosity is proportional to delta V squared, it's like if the velocity difference between the shells is the difference between either if they're almost co-moving, the velocity difference is small, but if one is stopped and the other is running into it,
Yeah,
that's a higher efficiency.
But it could also, I mean, whether the stuff gets unbound or bound is going to also depend if you don't have any like truly unbound matter that happens before the merger, then the amount of shocks as matter continues to plow out would shut off more abruptly, right? I think because at some point you'd run out of landmine.
That's right. So
to
in
collide.
these, we see circumstellar material essentially out to like 30 or 40 times the radius of the donor star, and not further. That may change with the particulars of things we're not modeling, like the accretion structure around the accretor. But that does mean that there isn't material in a like power law distribution out to infinity. Yeah, Phil.
Now, you didn't say much about the nature of the donuts. I mean, it looks like red giants, but I would like
Yes,
to
they're red here.
caution that the onset is very different whether you have a giant structure or radiative envelope.
Yes.
Like Nadia's models look like Hirschsprung gap systems.
Yes.
So they would have radiative structures.
Yes.
And the radiative envelope has very little mass.
Much more centrally concentrated.
And that's why the mass transfer initially, at least, is relatively stable. And that's why it's much longer lived.
Yes, so I've been looking at this in the case where it's initially dynamically unstable, but different sort of structures in the sense that like different degrees of central concentration. And what I find is by the time they come to things like the specific angular momentum of the ejecta are similar, so that, for example, if you integrate over this phase, there's a similar amount of material in the circumbinary environment. But the time scale is very different because one envelope is so much more centrally concentrated than the other. So the sort of number of orbits over which this takes place is very strongly sensitive to that structure. But like the integral quantities seem to be less strongly sensitive to that structure.
But I'm not even sure whether the radiative structures you can actually easily simulate, because I think this will be thousands of orbits.
Yes, so what I can do is look at a phase that is short enough that I can simulate in both cases. And in practice, that means picking a separation such that over hundreds of orbits something happens, because I'm not able to simulate for thousands of orbits. So putting them close enough that in X number of orbits there's measurable action is the only thing that we can do at present, and comparing across the two. So at, for example, 80% of the Roche limit separation, what's the rate of evolution? Those are questions that you can ask.
Other comments? Okay, let's thank all our speakers.